So let's go in the right order. So Soitec. Okay, I passed the movie, and if I can, okay. Soitec is a 30 years old company created by two researchers in 1992, coming from the CLAT. Okay, and we are manufacturing of engineered substrates. We like to say in our soil grows an amazing future because we provide unique performance to the components. So in a few figures, we have 283 patents filed worldwide each year, a total amount of patents of 3,700. All 13% of the revenue is dedicated to our R&D. We have 2,000 employees worldwide and a revenue last year of $1 billion. As I said, green innovation is key, and when you work on green innovation at the substrate and material level, you can leverage a lot of things because you are kind of agnostic, whatever the technology. We provide substrates for the power electronics, for the computing technologies, FDSOI, etc. So that's what we try to do. Sustainability supports value creation and strategy. We drive the transition to a sustainable economy with innovation and operation. We leverage our inclusive and inspiring company culture and act to become a role model for a better society. That's the picture of the company, so you can see the Alps. And we are very near from STMicroelectronics. It's the factory of Kroll is something like 100 meters on the other side of the river. We are implanted also worldwide. So in France, in Bernin, we have a small capacity of production of gallium nitride in Belgium, and another big factory for 300 millimeter in Singapore, and other are mostly support and sales office. For the market, so this now you are very used to that. I take the advantage to say that we have a table here. After you can come, we will show in reality what is the value chain, so you can really concretize what is the value chain. So we provide the engineered substrates. For these three markets, basically, our SOI is today in 100% of the smartphones. There is no smartphone without RF-SOI. It replaced the gallium arsenide technology starting in 2013, 2014, but Cécile will talk a little bit more about that. So Connect is one of our main division, automotive and smart. That are the key drivers for our technology development, and that are also the key divisions. So our companies is divided into these three divisions to have a focus on the market. So we have the Connect division with the main drivers of 5G millimeter wave, 5G sub-6 GHz, mobile infrastructure, Wi-Fi 6, and several products of Soitec, RF-SOI, Connect, POI, piezo on insulator, which is for filters, FDSOI, and gallium nitride. We have the automotive division with the main drivers of autonomous car, electrification, infotainment, and Industry 4.0. Of course, you will find the SmartSiC that I already talked about for the electrification, Power SOI, FDSOI, and gallium nitride substrates. And we have the smart division with the main driver of edge computing, 3D sensing, smart home, and smart city and data centers, where you will find the FDSOI, smart FDSOI, photonics, partially depleted SOI, and imager SOI. Basically, this is a little bit to go more in detail, so I don't come back into these slides. That's just to detail what I just already said, and you can find the pictures of the different technology substrate that we provide. So for instance, the SmartSiC that I already talked about, this, and the other advanced engineered substrates that we propose for the different division. And of course, beyond these products that are already running, that are in 100% of your smartphones, we have an innovation toolbox. As you already understand very well, the smart cut, but that's not the only technology. We have the smart stacking, enabling to stack components on top of and make different layers. We have the refresh, repolish, epitaxy, material expertise, advanced processing. I don't come back on this smart cut slide because I extensively talked about that. But basically, we can bond and we can smart cut quite everything on anything. And we can target with the different material, wafer A and wafer B, different applications. So you see the added value of the substrate material. For instance, the smart SiC, this is the conductive bonding capability and the fact that the polysilicon carbide here is very low resistivity. So the conductivity is very good, and you have gains at all the levels of the value chains. Green Deal compatible technology. As I said, this is rejecting 4 times less CO2 than the state of the art. But at the same time, the manufacturer of components and the system makers, they can have modules smaller because the conductivity is much better. And at the end of the day, and I have to say that now, if you submit a European project, I mean, if you want to be funded in a European project, you have to stamp to be Green Deal compatible. You have to bring, because you will be very challenged concretely with deliverables, what is the total gain in the value chain that you provide of your technology in terms of Green Deal. Now, Europe really wants to fund greener technologies. And we can go beyond with the wafer A, the active layer. You can choose silicon, of course. Piezo material, silicon carbide, I already talked. Indium phosphide. Indium phosphide for the 6G, for the very high frequencies. We have very interesting tiling approach. Gallium nitride, gallium arsenide, germanium, and you can bond this on handle carrier wafers, silicon, sapphire, SiC, gallium arsenide, or device wafer already existing. That's our toolbox, and the innovation is playing with this. Yeah, and in the IPCEI number 1 that Patrick already presented, we are in the TF1. We are energy efficient chips with 3 substrates: FD-SOI, RF-SOI, and POI. FD-SOI will be presented by Philippe. RF-SOI and POI will be presented by Cécile. And tomorrow you will have a presentation of the Smart SiC by Walter. So we are in the TF1 energy efficient chip and in the TF5 compound material. But now with the new IPCEI, as I explained, this IPCEI is different. It's 5 work streams and 19 member states today, but soon there will be Sweden, so we'll come back to 20. And you see the number of projects is increasing. We have FD-SOI, 2.5D, 3D stacking for the think approach. We have in the communicate the piezo insulator for 300 millimeter. We have the RF-SOI next generation for a millimeter wave 5G. We have FD-SOI plus high resistivity base to have increased performance in terms of RF, gallium nitride on RF, indium phosphide, and advanced photonics. And of course, we have this new smart SiC substrate for the electrification. And this is really an incredible dashboard for me, for Soitec people, to create links with equipment, material, process, foundries, IP design, and system actors. And we can create these links and build this ecosystem, strengthen this ecosystem, also in parallel in the European project like CADITI. And that's it for me. Jean-Christophe.
Oops. Okay, so quick. ST. So where are we? So we are, you have understood, we are making, we are designing, and we are manufacturing semiconductor. So we are a big company, 48,000 people in the world, almost, let's say, 8,400 people working in R&D. Okay, we have 14 main manufacturing sites. Okay, we are implanted almost everywhere. So for you to know, in Europe, we are making the process of the wafer. So the technology on top of the wafer. And in Asia, we are making the process of the packaging. Okay. So some word of vocabulary, the process of the wafer is called front end, and the process of the packaging is called back end. This is the word in the semiconductor. Okay, so front end here in Europe, back end in Asia, mainly. So what are we doing? So we work mainly on very long-term trends, so smart mobility, of course. So to have car more secure, greener also. We work a lot on power and energy, so SiC component, GaN component, or also silicon component, where we need still to make progress. There's still some place for improvement. And of course, we provide also many chips for Internet of Things. So it's many things, so microcontroller, RF component, many things for 5G and so on and so on. So you can find us almost everywhere. Okay, so the four markets we address, so automotive, okay, industrial and home, personal electronic, so Face ID, for example, and many things for communication, so 5G, 6G, and so on. Okay, the kind of component we are making, so MEMS, microelectromechanical system, okay, FDSOIs, analog RF CMOS, ENVM stands for Embedded Non-Volatile Memory, so memory, okay. Smart power, so special logic for power technology, discrete power, vertical power, optical sensing, of course, and of course packaging. So we are making everything, very good. So we are a large company, we have many customers, almost 200,000. So the top customers are this one, so you can read it. So we have very large customer, smaller here, and then we distribute our components through the distribution network. So we can find, for example, microcontroller ST almost everywhere. If you go to Arrow, Avnet, and so on, you can find our products. So this is a way of distributing our products also. Okay. Sustainability, so of course we are concerned with the sustainability, so we do many things. First, we take care of where we source our material, how we design the material, how we manufacture, because the manufacturing of a semiconductor is very expensive in terms of energy and water. So this is a real issue. So we are trying to do our best effort to minimize both things. Okay, and of course we provide technology which are, okay, let's say environment friendly, because when you provide some SiC or GaN component, for example, if you deploy this kind of technology at very wide scale, you can save some energy plants, so carbon plant or nuclear plant. So this is very important. And of course, we take care also of how we can recycle our components. So this is very important for ST. For instance, also ST intend to be carbon neutral in 2027. So we will work on that. Okay, ST in IPCEI. So what we are doing, two main things, digital transformation, energy transition. So we will find again our four pillars. So we work on digital chips with low consumption, power chip very efficient, imager with AI, and RF radio frequency chips. Okay. And in parallel of all this stuff, we are working on the production system or on our factory to make them more efficient, more energy consumption, and less energy consumption, and so on. So this is very important. We work on the design of the technology, on the way we produce it. The both things. Okay. for some example of main achievement in IPCEI 1. So we are talking about microcontroller. So our target is to have more powerful microcontroller, ultra low power microcontroller, and also full of connectivity. Okay, to have very autonomous component. So this is, and we do on 40 nanometer. 20 nanometer is the size of the gate of a transistor. 40 nanometer, 33, 28, and we try to go to 18 in the next IPCEI. Okay, so this kind of components, of course, we want to also develop FD-SOI again. So we will make microcontroller with this FD-SOI, of course, but we want to use it for automotive radar, so new microcontroller with embedded memory, and also with 18 nanometer. Okay. Then we go to the power side. So here we work with SiC, so in 150 millimeter wafer size. We work on 200 millimeter GaN wafer size, okay, in Tours. We have demonstrated that this technology is okay. And we have also made many things. So Sarah Louis from ST will talk about that. Tomorrow, I think, we will speak about the BCD technology with a special kind of technology for power application. Okay, and then for the sensor, here we are making optical sensor. And the main target here is to have a sensor very powerful, very integrated, and very compact. And the way to do it is to stack wafer. So we have one wafer for optical, one wafer for logic, one wafer for memory, for example. And we stack up to 3 wafers on top of it, like this. So it's an example of 2, photosensitive wafer plus logical sensor. And at the end, we have a sensor integrated. Very easy on a drawing, not so easy in technological to do it in the fab. Okay, and we can do this stacking up to 3 today. And we are working also with for other type of sensors. So, for example, for inertial sensor, you will have some explanation tomorrow also. So, inertial sensor, also piezo micro mirror stuff, so actuators. Okay. And finally, for RF, so we are making RF chips. So the goal of the game is to go higher and higher in frequency to save energy, because the more you use, the more the component is able to go high in frequency. You will use it at low frequency, and you save energy at the end. So here we have made first demonstrator of silicon by CMOS technology up to 600 gigahertz, which is not bad. Okay, on two last slides regarding, okay, we are making our job in IPCEI, so ST internal, but we are making this job also with partners thanks to collaborative projects. And here, I will not read everything. So here you have the name of the different projects which were induced by IPCEI and supported by IPCEI. So it is collaborative projects. So each time you can see in green the number of partners, and here it is the number of countries involved in Europe. So you see that there is plenty of opportunity to do something with us here. And here also other kind of project for RF power. And that's it. I am done.
Ça va aller, c'est bon. Ok.
C'est bon?
Thank you. I'll try to be quick. So Lynred now. I'll talk about the company first and what we do in IPCEI, the projects we have in this. So who are we? What do we make? What market application do we serve? And the challenges we have? That's what I will show you right now. So Lynred. We are owned by 2 big French companies, Thales and Safran. And we have a unit in the US and in Asia for commercial technical purpose. The main company, the main plant is in Grenoble, where we are about 1,000. Some key numbers here. 50% of revenue is dedicated to R&D. And that's very important. That's the way you stay at the edge. We sell sensors, infrared sensors. It's not as widely spread as visible sensors. So we are very proud to say that we sold more than 2 million detectors since we were created. But if you look at those numbers in the visible range, it's billions that are sold regularly. So I'll go quick. We are the result of the merging between Sofradir and Ulysse. So we have basically two technologies which are cooled and uncooled sensors. Just a quick word about where we are. That's Grenoble in the center, and that's all the companies which are involved in imaging in the valley. You see that it's a very, very busy place for imaging technologies. And you see ST, you see Soitec here, Lynred over there. So we are not on the same side of the valley. It's a nightmare to go from one place to the other with the traffic. So we make, so back to basic, the physics. Every body emits infrared lights. It depends on the temperature of the body. Well, the wavelengths depend on the temperature of the body. The sun, 6,000, all the light is emitted in the visible range. That's good news because that's what we see. For lower temperature bodies, human body, for example, 37 degrees C, it's 10 micron wavelength range. That's the maximum. And so you see that without external light in the infrared, because every bodies emit light, we can see if we are able to detect the right wavelengths. So that's what we do. And we cover the wavelength range from SWIR, 0.8 micron, up to 14, 15 microns. And we have two technologies, that's what I said. One, where we use photovoltaic detectors, meaning that every photon creates electrons and holes. It's a photodiode, and that's what we detect to make the signal. And we have another technology, that's the microbolometer technology, where we have MEMS, very thin membranes that are under vacuum. When they absorb infrared, temperature increases, and we detect the temperature increase. So it's totally different mechanism, but it works for the Luire wavelength range. And what we do, so in the end, is this. You saw already some pictures of a product. So it's either the small sensor here, uncooled sensor, or the big one here with the cooling machine for high performance sensors. I won't go further into the detail, but if you want to know more about infrared and what are the parameters, the important parameters, you can go on our website, and we have an e-learning module, and you will know everything about NETD, pixel pitch, and so on. It's interesting. Not too long, but interesting. So what type of markets do we serve? I already told students this morning that applications are really, really multiple. So we summarize here in 8 segments. Aerospace, we have sensors in satellites, defense, surveillance, security, thermography for example, building management, outdoor activities, machine vision, so that's the industry use of infrared for monitoring process, for example, smart building, and transport and mobility. So a few examples, security. So at night, even without any visible light, you can see if people are trespassing. That's on the top left, trespassing barriers, for example. Here on the right, so the left part is visible light, the right part is infrared, at night, you can see that it's very, very difficult to see a cyclist, pedestrian on the road in visible light, because you have the car coming in front, and that's very difficult. Here with infrared, it's so much easier. So this is a technology that will be used more and more in vehicles. And smart buildings, infrared allows to detect how many people are in a room. And so if you have a full building equipped with this, you can adjust temperature, air conditioning, light, and everything in the building and save on the energy. So that was one use of infrared. Basically, you collect everything and you make an image of it. There is another way to use infrared. It's to look at specific wavelengths in the infrared and to extract other type of information from this. So in the center, for example, you have an absorption spectrum of different types of plastic. You see that if you are able to look at different wavelengths, you will be able to differentiate between different types of plastics, for example, and recycle the plastic. So sort out the plastic and recycle efficiently the plastics. So that's one other use of infrared. For medicine as well, you have information about tissues in the wavelengths. This you saw already, that's methane detection with the multispectral sensor, and there are other applications in space as well. So challenges we face. I think it's the same for every company. No matter the technology, customers always want smaller size, weight, and power, and price as well. So that's a big challenge, and that's what we've been working on in IPCEI. And here are a few of the parameters we worked on improving: number of pixels, the resolution, the sensitivity, the crosstalk between pixels so that the image is more better defined, noise, frame rate, and so on. So that was the work in the IPCEI we did. And this is in 3 different projects that we will talk about tomorrow. You will see results about these 3 projects. Very high performance detector for astronomy and space application, high operating temperature sensors for swap applications, and low-cost small pitch modules for automotive and smart building. And last slide, which is also the collaborative project that we have. We do a lot of work ourselves, but we also have a lot of collaborations with European partners. And here are a few projects that we had in the past. And Brighter is the very last one that's going to start in December. 16 partners, 5 countries. It's going to be a very interesting project on microbolometers. Thank you.